Lorianne just mentioned, I recently graduated with a master's in biology from the University of Wisconsin here in La Crosse, and they were very accommodating of me studying this sort of intersection of textile history and biology. And I think that these conversations between science and museum studies and folk art are really interesting and fruitful. And I would love to see more of these collaborations between different organizations in the future. So I'm going to go ahead and get my presentation going here. Today I'm presenting some of the research from my master's thesis, where I explored non-destructive techniques for determining the dye used in historical textiles. I focused specifically on Orchil dye, and I also examined some species of lichen here in the driftless area that can be used to make this really significant special dye. I'm interested in these human-fungal interactions and also how immigration and industrialization altered these relationships. So to answer these questions, I was lucky enough to be able to examine some pieces in the Vesterheim Collection for my work, and I thought that some of the Vesterheim audience might like to hear about it. So for those of you joining outside of this area, the driftless area refers to around 24,000 square miles in southwest Wisconsin, southeast Minnesota, northeast Iowa, and northwestern Illinois. So this area is called the driftless because it did not experience that glacial drift that created the flat areas and the glacial deposits that sort of make up most of the Midwestern topography. It is also a refugia for many species that persisted in this area during the last glacial period, so it's really interesting from a biological perspective. And both the Vesterheim Museum and the University of Wisconsin-La Crosse are located in the driftless area. So let's get a little bit deeper here. What is Orchil dye? It's a historical dye. It is made from some species of lichen, and it's one of the most significant sources of purple dye before the introduction of synthetic dyes in 1856. Historically, purple has a weird and shifting definition, so this dye can also make reddish and bluish colors. It is made from lichens with a really specific internal chemistry. Lichens with this chemistry are found in many genera across the world, so they're not limited to one geographical region. They're not limited to one specific species or even genus. In Norway, this dye is called korkje. That is spelled Korkje. And there's a bit of writing available in English regarding this dye and some specific discussions in a Scandinavian context, largely written by lichen dye expert Karen Dietrich Castleman. I can happily share some of those resources during the Q&A. As I mentioned, this was a significant purple dye before synthetic dye, but it was also significant before some of the organic dyes that we think of as purple. Cochineal being, famously a red dye, but also giving us some purple hues. It predates that by quite a bit outside of the New World. I will also mention right now that this large-scale harvesting of lichen, historically at an industrial scale, contributed to lots of population decline. It's a really slow-growing organism. There's some evidence that lichen species sampled in medieval objects may be extinct, as there is no direct match. So here's a little bit of a timeline for us. So as a species, we have been dyeing fabric since at least 10,200 BCE. So that is quite a stretch that we have felt compelled to dye our fabric. Over here in 593 BCE is the earliest mention of purple dye from lichens. And then around 1300 to 1400 CE, Florentine merchants revive this Orchil trade, so it becomes a really booming business. And then all the way here at the end in 1856 CE, a man named William Henry Perkin accidentally invents the first synthetic dye, which is called movine, and just happens to be a really similar color to what you might expect from Orchil. After that first synthetic dye, we rapidly see development of other synthetic dyes, and that is obviously most of what we use on an industrial scale today. Synthetic dyes are predictable, they're light fast. What you see when you're ordering is exactly what you get, which cannot be said about very many organic dyes. So, as you can see, I've added a little point here. This little orange dot is where most Norwegian immigration to the US occurs. So somewhere between 1825 and 1920. We have a new dot here. That is when cochineal is first exported to Europe around 1523. So again, though cochineal is also a significant historical dye, outside of the New World, it is still fairly new when we consider this entire timescale. I can't talk about purple dye without mentioning Tyrian purple. This is possibly the most significant historical purple dye. This is the dye made from mollusks. The earliest evidence of Tyrian purple is from 1600 BCE. And there is some evidence to suggest that Orchil dye was originally added to the Tyrian purple dye vat, either to shift the color or as an extender. And it is possible that due to the population decline of the mollusks, it may have gradually overtaken the primary ingredient. And again, all of these dye industries were devastating to the organisms being harvested. So this is a really important consideration when we have the organic versus synthetic dye debate today, at least regarding slow-growing organisms, because those mollusks were also greatly over-harvested to make the Tyrian purple, which again may have contributed to the rise of the Orchil dye. We need to understand a few things about lichens before we move on here. So a lichen is a symbiotic relationship between a fungus and a photosynthetic organism. That can either be a cyanobacteria or an algae, or sometimes both. The fungus is not picky. This fungus provides shelter for the photosynthetic partner, whatever it may be, and it receives the energy generated through that photosynthesis. The fungus is getting a better deal here, we're pretty sure, but there's a lot that we don't know about this relationship. The fungal partner is unique to each lichen, so that's generally what we use to identify a lichen when we're using DNA testing. The photosynthetic partners can repeat across genera. There are 4 basic morphologies for lichens. So they can be crustose, they can be fruticose, they can be squamulose, or they can be foliose. There are also a lot of morphologies situated in between these 4 basic growth patterns. The chemistry that creates Orchil dye exists in all 4 of these morphologies, so it's good to narrow down what morphology grows in your region if you are considering looking for these lichens. And again, if you do go harvesting, just remember that they are really slow-growing organisms, so the only real way to take these without leaving a footprint or having an effect is to take things that are totally detached from their substrate. It's nice to go out after a storm. So my research, because I'm in the driftless area, is primarily concerned with lichens and foliose families, specifically Umbilicariaceae and Parmeliaceae. One of the Norwegian species of Orchil dye lichens is crustose, but since my fieldwork was all done here, I didn't worry about the crustose forms. So what is a secondary metabolite? These lichens create secondary metabolites, which are organic compounds that are produced by an organism that aren't really directly required for its normal functions. So they don't have anything to do with growth or development or reproduction, but they serve some sort of ecological function. So sometimes they are defense against disease or predators. Sometimes they are an adaptation to the environment. Many of the dye pigments in plants and lichens can function as sunscreen. So lichens can live in really harsh environments, like on rocks in the sun or on trees in the winter when the leaves are gone. They can survive in the Arctic. So that is primarily where we are seeing these secondary metabolites in these lichen species. And these secondary metabolites are what are responsible for our Orchil dye components. So you're already familiar with some really prevalent lichen secondary metabolites. If you have ever used a perfume with oak moss in it, oak moss is derived from the secondary metabolites inside of the species Evernia prunastri. And if you have ever done something in a microbiology lab, or if you've used litmus paper to test the pH of something, you have encountered Orcean stain. That is derived from various species, and that is the product of the process I am talking about today. So the same species that can give us Orcean stain are the same species that can give us Orchil purple. The way these lichens make their purple dye is a little bit time consuming. Obviously, we're making the purple dye from them, but we put crushed lichens in a jar and cover them with ammonia and water in equal parts. This jar is regularly opened to expose the solution to oxygen. So I don't know if you can see this. We'll get a better look later when I'm not also screen sharing. But this is the finished vat. This extraction is done. You can tell because it looks like grape juice. So these secondary metabolite starting points for Orchil dye can be gyrophoric acid or lechinoric acid. And over time, when we put these crushed lichens in a jar and cover them with ammonia and water and regularly open the jar to expose the solution to oxygen, that ammonia will promote the breakdown of these components into orsolinic acid. So as they're exposed to oxygen, more complex reactions build up these larger dye structures. And at the end, we end up with dye molecules in the Orcean family. So it's important to think about this dye as a family because we get slightly different outcomes based on species, based on condition of the lichens, based on age of the lichens, based on water quality. There are a bunch of things that are going into this reaction. And so, as you can see in this image, we're getting slightly different colors. We can also tweak that a little bit further with the chemistry of our dye vat. But right off the bat, two different species are going to give you two different colors. So this process hasn't changed much over the years. That's pretty much how it's been done. A notable exception is that we now use ammonia instead of urine. I think some people still use urine. That's a personal choice. I am not that much of a traditionalist. So as I looked into potential non-destructive identification methods for historic lichen dyes, there are actually some existing studies that are looking at Orchil dye on historical textiles or in paints or illuminated manuscripts. And this literature uses much more advanced and prohibitively expensive and not portable tools. So they're more accurate, but I think we can get pretty close with cheaper methods. This existing Literature also does not make comparisons to New World species or to synthetic dyes, as that wouldn't be relevant to the artifacts they're studying. However, if we are looking at items in the Vesterheim Museum, if we think about that timeline of immigration and the invention of synthetic dye, we're also really in that sweet spot where people may be doing things traditionally, or they may be adapting these new methods. So if we think about, the bulk of the household dyeing would fall to women who are also really busy with just a few other responsibilities around the home. Synthetic dyes may have been adopted by households as soon as they were available. So while I think we tend to romanticize some of these folk art traditions, especially when it comes to dyeing, this may have not been, it may not have been important as to how we were getting our purple dye. And so that is also something I wanted to take a look at. This research was a partnership with the Vesterheim Norwegian American Museum, so I was able to access the collection on several occasions and take readings of the surfaces of various textiles in the collection. Orchil dye is very significant in Norwegian textile history, and there are some objects that were believed to be dyed with orchil. They were visually confirmed by Lichen dye expert Karen Castleman, and I wanted to be able to offer this molecular data to sort of back up what was already visually confirmed. So I think that that is a really potentially fruitful partnership for many biology departments and archaeology departments in various universities between those institutions and the museums, because this does add a sort of extra dimension to the collection, as well as consideration for the future when maybe some of these objects are not able to be handled anymore. We have to think about a museum collection the same way we as biologists think about an herbarium or a fungarium. There will come a point at which you would rather not handle those specimens at all, or also some of that physical structure may degrade to the point where you're not able to get an accurate reading of it or a DNA test. So it's nice to be able to back up some of these collections while we are still able to handle them, and just to kind of have that information in the long term. So it's important to use a non-destructive technique because we don't want to destroy these items in any way. A lot of sampling techniques will require a thread or to apply something to the surface, and we don't really want to do that to these pieces. So I was able to use a technique that does not require any portion of the textile to be destroyed. I also compared them using a statistical analysis tool that uses similarities to see if I could make connections between these unknown dyes and then known synthetic and organic dyes that were historically likely for these specific pieces. So I will let Lauren hop in here and talk specifically about that visit from Karen Castleman and how these pieces were visually confirmed.
I was contacted by Karen, whom we knew about through her book, Lichen Dyes, a New Source Book. Karen is a dye expert from Nova Scotia, and she was curious if Vesterheim had any examples in the collection of purple textiles or purple yarns and textiles. And once she arrived on site with her giant ring of dyed samples for us to compare to the collection, I was really surprised how many textiles in the collection had some purple yarns. It was also very exciting to see her put down this ring of dyed samples and almost see some of the yarns in our artifacts disappear because they match so closely with some of her samples. And on the left on the screen is a sample It's a woven coverlet from Østerdalen in eastern Norway, and it was brought to Iowa. And we had it laid out on the counter. She set down her ring of samples, and one of them matched perfectly. So it's the center sample in about the center of the ring there, and just to the left of it is this sort of same soft, warm, rosy pink color. What was exciting for me was that she had many different shades. And so when we were looking at pieces in the collection, some of them I might not have called purple, as Jane is alluding to, that some of them might have been considered red or considered almost blue. And to get this visual comparison was really very, very useful. Even more exciting, I think, than the pieces that we know came from Norway is the opportunity that this visual match and now the scientific non-destructive match offers a museum like Vesterheim is a chance to understand more about what was brought and what was created here. And so, Jane, I think you've got another slide for us that shows a few of the pieces that we asked Jane to sample when she was at Vesterheim with her equipment. And I'll just mention briefly the history of some of these pieces. And the first is on the left. And this is a detail of the dress that you saw earlier. And you maybe thought, well, this dress looks all brown. But underneath the arm, in the pleats, where it was not so faded, the stripes that look like they're light brown are actually fairly striking purple. This dress has a lot of mystery to it. We don't know much about it. We know that it belonged to a woman who had come from Telemark in southern Norway. She came at the age of 23 in about 1859 and lived in Oconomowoc, Wisconsin. We don't know if she brought the dress with her, if she brought the fabric with her. The style of the dress doesn't quite answer the question of, is this Norwegian made or American made? And understanding more about what people were bringing their lives in Norway, but especially what they were making and doing here in the United States is all about what we do here at Vesterheim. And so we've been so interested to know more about this, but previous opportunities would be destructive tests. And so we had a visual comparison with the samples from Karen Diedik Castleman, and we're excited to know more from Jane. In the bottom row, the striped textile is what we call a shinfell. It's sheepskin on one side, large pieces of sheepskin sewn together, attached to a woven textile for warmth. And this is a traditional Norwegian and Scandinavian form. This particular one was made in the United States, by an immigrant who had come from Hedmark in eastern Norway and came in 1888 to Jackson County in southern Minnesota. Each child in the family received one of these as a special gift. And so this one was made for a daughter, Ida, for her wedding in 1912. The history is that this was woven in Minnesota and made by Thor Flatgard, the husband of the family. And certainly in Norway, we know that sewing the sheepskins was traditionally men's work. We don't know if he actually wove the textile or not, but the family information is that he had made this. So this is an opportunity for us. We're fairly sure this really truly was made in the United States. So what kind of dyes were people using? What kind of things were people weaving? We know the Flatguards had a loom in the United States. And so this helps us understand men's work, women's work, and life in the United States. The rest of the pieces here on your slide come from one family. This is a family that had come from Gudbrandsdal in eastern Norway to southwestern Minnesota in 1867. And it was a mother and a father and two of their four children. We know that the mother had a spinning wheel that she brought with her. We know that she did a lot of needlework, weaving and spinning and knitting, but we don't know exactly with some of the textiles if they were made in Norway or the United States. We also don't know if some of these were made by her daughter, Mari, who is known to be an excellent needleworker. So once again, the information from the dye tests could help us understand more about the textiles themselves and the people who made them. So we've been so excited to learn more from Jane, and I'm learning for the first time today on the program. So you'll be learning when I am too about the source of some of these dyes.
Thank you for that really useful background. This is why these collaborations are important, because I can contribute a little bit of insight, and Lauren's got the insight that the pieces came in with, as well as, everything she knows about Norwegian textile history and immigration. And together, it's really nice to sort of put these pieces together for a more comprehensive view of these artifacts. So I used a tool called an infrared spectrometer. This is a tool that identifies the surface it is looking at by using infrared light. And it is really focused on what kinds of bonds we have, which can tell us about the chemical identity of what we are viewing. And this is fairly portable and fairly inexpensive compared to high performance liquid chromatography, which is what a lot of existing studies are using. So we are, with this tool, identifying the compounds by measuring their interaction with infrared light. So each of these vibrations are at a different frequency, the vibrations of the covalent bonds, and that tells us about the structure of the dye molecule itself. And this reads out as a spectrum that can be then compared to spectra from other dye samples to determine the differences. So we used an undyed sample to subtract the substrate, in this case, the dyed material from the spectrum itself. The substrate was taken from the undyed material on the sample if possible. So whereas like some of these socks, if you're looking at them, are the yarn is dyed using an ICAT technique. And so I would sample the red and then I would sample the white, so some of those undyed spaces, and then I would make a subtraction of that white from the red so that what I'm left with is just the red, the spectrum from the red yarn. And I sort of grouped these by chromophore when I looked at my data. So the chromophore is a specific part of a dye molecule that is responsible for its color. This does not mean the color is determined by chromophore, but this is a good way of looking at the dye structure. So once I had all of those spectra, I essentially had a number for the significant wavelengths of each piece. And I put them in with a bunch of spectra from known historical dyes that were possible, so both organic and synthetic, that would have existed around this time frame. And sorry about that. I essentially turned it into a presence absence for each peak. So did this sample have something here? Yes or no? I pulled this into R, which is a programming environment that's mainly used for data analysis. And I used a technique called association rule mining. This is also called market basket analysis. So if you're familiar with that, this is how corporations use your store receipts to figure out how to group things together in the store based on how often one thing was purchased with another. You might then see those together on an end cap if they're really commonly purchased together. For example, during flu season, you might see NyQuil and Kleenex on the same end cap. Well, that's because they looked at everyone's receipts and said, okay, well, in November, everyone seems to be buying these things together. So we'll make decisions based on that. This analysis essentially generates rules. So how often things show up together based on how many times they appear together in the data set. So in this case, it's how often they share peaks. And this was able to group things based on similarity for me. So this is what a rule looks like. The one that is highlighted is saying if sample V119 shows up, then sample V94 is likely to show up. And these are sort of the analytical, support numbers for that. Lift is a measure of the strength of each rule. So the higher the value, the stronger the association. I'm a visual person. This particular grouping doesn't work super well for me, but this works really well. So I can also visualize my association rules as a network. And this is telling me how similar or how likely these dyes are to show up next to each other in this data set. So it's a little clustered in some areas, but let's zoom in on one specific area. So here I have sample V94 kind of acting as a hub to these other dyes. So this is a good indication that I need to zoom in a little bit further on this group to see what's going on. And when we do that, we have sample V94, so those sort of fuchsia stockings that were previously confirmed visually as Orchil dye by Karen Dietrich-Castleman. And then I also have showing up in that association sample V119, which is a known lichen dye sample from a book of dye samples made at Voss Husflidsskole in 1972. So for those of you who aren't familiar with these schools, these Husflid schools are traditional handcraft schools in Norway. This one was in Voss, Norway. And these are a really, really close association. They showed up together often. So that's a good indicator that I need to then compare their spectra. So these are the spectra that were generated by that infrared spectrometer. And this is the stocking on the top and the sample from the book on the bottom. I've highlighted the peaks that are really, really strong matches. So this is really good. This is telling me that these are really, really similar chemical structures. I can also compare the sample of interest, here the stocking is again on the top, with known lichen dye samples of specific species. So remember that we're getting a slightly different chemical composition from our Orchil dye baths. So it is possible that we can also determine which species was used to dye something. And in this case, the spectra on the bottom here is Umbilicaria mammillata, and that is a really, really good match to me from this top species, or this top sample. So there are a lot of ways that we can sit with each of these pieces of data and sort of zoom in further and further and answer some of these questions that we have about specific pieces. Other pieces that were very likely Orchil dye were the purple dress. It is not from the family that own the stockings, as Lorianne indicated. And then also one of the balls of red yarn, but not the others. And so that is another thing that we run into when we're studying dyed objects, is that dye can very often be several dyes in one vat, or something that's been over dyed, or maybe one dye didn't really take, so we save that ball of yarn and we re-dye it with something else. Well, we still got a little bit of that bond on the surface from the previous dye. And there are a lot of things that we want to dig into a little bit further here. So hopefully we'll be able to take another look at some of these pieces in the future. But like I said, I also included synthetic dye in my data because I knew that some of these were likely to be synthetic. And so we saw that the red of this apron, as well as the red of the main red of these socks, the heels are a different red, if you'll notice, and we saw that pretty often in the stockings. So the main red in these socks and the red in the apron were likely the synthetic dye Bordeaux red or some closely related dye. I also wanted to see if these dyes could be grouped by color or chromophore. And without getting too deep into this figure, they don't. They don't really group by dye or by chromophore. So dyes are designed to create a specific color that will successfully bond with a specific substrate, which is why some of your at-home dyeing projects have failed miserably, because something that is designed to chemically bond to a protein surface, right, like a wool or a silk, we all know when we try to dye a cotton t-shirt with that dye and don't make any adjustments to the dye vat, that's going to be really disappointing and probably a waste of a t-shirt. So chromophore is a huge part of the picture here, but it's not the whole picture. And like I said, dye recipes can also combine ingredients from multiple sources. And we also have the oxychrome, which is the other component of a dye molecule. So those are chemical groups that are added to the molecule to adjust the shade and the intensity of a color. So there's a lot going on chemically with each individual dye. But like I said at the beginning, the end products of these dye vats are dyes in the Orcean family. So it can also be difficult to tell when things are related, if they are pretty different in end product. So for example, here is a comparison of peaks between commercial Orcean on the bottom, so from like a scientific supplier, and a precipitated dye pigment that I made with Umbilicaria mammillata. So they're chemically the same product, but only 2 of the 5 Umbilicaria mammillata peaks would have even aligned with each other in my analysis. So it is also possible that there are some Orchil dyes in the samples that just didn't line up the way they needed to in the data set. This can be really confusing when trying to confirm if a textile is dyed with lichen or not, but we may be able to use these differences to our advantage. So because we get so many different outcomes, it may be possible to determine to the species level. And that would be really useful if we want to compare or ask the question, was this textile dyed in Norway or was it dyed in the US? Because we are going to get different Orchil dyes from different species. And since lichens are, at least some significant ones, are limited geographically to Europe, to North America, to one specific pocket of North America, you can get kind of specific. That may be able to tell us whether something was dyed in Norway or in the US. And this comparison really explored the domestic use of synthetic and traditional dyes during this time of adoption of synthetic dyes at the industrial level. So, like I said, this synthetic dye may have been really useful for women after immigration to North America. Now, when you go out and you want to identify lichens, here are, the top 2 lichens here are the same species, and the bottom 2 are different species. I don't know how you guys feel about lichen morphology, but very few people are confident enough to identify these based on how they look alone, right? So when determining what lichens may have been used by people in this area for purple dye and thinking about whether or not these Norwegian immigrants who were used to making purple dye from lichens in Norway would have come out into the woods here and tried to reestablish that natural interaction. The first sort of checkpoint there is, are they comfortable identifying them morphologically in a new environment? These are not species that are in Europe. These are not species that are traditionally used. Sorry, these are not species that are traditionally used by Norwegians for purple dye, but I do believe that some of these may have either a presence in Europe or closely related species in Europe. Let me not misspeak there. But these are not known in Norway as Orchil dye. So No, obviously, we are not going to go out. I don't even want to go out and identify these based on morphology alone. But it does get us closer to figuring out what can be used for orchid dye. So I know that the ones I'm looking for in this area are going to be foliose. I know that they are mainly going to be in the genus Punctelia, which is grayish. There's a greenish close relative called Flavopunctelia that has the same sort of broad morphology and also contains lichens with the chemistry I'm looking for. So in the field, there is a quick way to tell if they have the chemistry that is going to create an or kill dye after an extraction. Bleach is what we use for this test. We call it the C test. I actually use an empty nail polish vial that I fill with bleach and then use the brush as my bleach applicant because you don't want bleach in your pocket in some weird bottle you found while you're walking around, unless you really don't care about your clothes. So when we do these tests in the field, we apply bleach to the medulla, which is white. So if you look here on the anatomy figure, that is going to be the area just underneath the photobiont. So we scrape away that top layer, and then we get to the white medulla, and we just apply a little drop of bleach. And you can see here on the right, that is a positive C test. So that means that we are looking at a lichen that has the chemistry capable of creating or-kill dye. So I wanted to know what was in this area that could create or-kill dye and what species specifically we had. To do that, I needed to verify what I visually confirmed to be specific species using DNA extractions. I won't get super deep into that here. But I took DNA extractions for all of the samples I collected and I sent them off for sequencing so that we could look at this one specific region of the rDNA that's really different between species so we can use it to confirm the identity of the lichen we're looking at. Here's sort of a breakdown of what the database said that my DNA ID was, as well as some of the spot tests I did. Geographical range is also really important to consider. Like I said, lichens are really grouped geographically. And so you sort of know if you get a DNA test telling you that it's one thing. If that thing isn't found at all in the area that you took the sample from, then you're probably dealing with a misidentification in the database, which is common for lichens because, as you saw, they're difficult to identify. My sort of takeaway thought here, though, is that looking at these two lichens, which are the most prominent historical sources of or-kill dye in Norway, neither of these would be recognizable. Neither of these are in this driftless area. And so I don't think that any of these would be recognizable to them as dye lichens. And I doubt that they had the time to put a bunch of different lichens in a vat and sit around and wait for them to turn purple. So my main conclusion here is that I think that really we're looking at a pretty significant turn to synthetic dye post-immigration, at least in this area. And I will just end with a little picture of us working in the library. You can see how portable that equipment really is. And with that, I think it's time for some Q&A.
Thank you so much, Jane. That was just a fascinating presentation. I feel like I learned so much. As we wait for questions to roll in, do you want to show us the vat again?
Oh, yes.
And
Okay.
you'll be using this in your class that you're teaching next week?
Yes. So this is for our lichen dye class next week. So here is a finished, ready-to-go vat of Umbilicaria mammillata. And then I also have a finished extraction from Lacellia postulata. This is one of those Norwegian species. So these are actually pretty closely related lichens, but you can see that they really have different colors already. So that's kind of an exciting thing about lichen dye. And also you can see how concentrated these are. You don't need very much of this at all for a very vibrant dye vat. And you also do not need to, you don't need a mordant for dyeing with lichens, which is something that's really exciting because, you get to skip a step and get your color a little bit faster.
Wonderful. As you showed that, we had a couple questions pop in about making the vats. First off, how long does the extraction typically take? And do they give colors of green or brown, or is it just kind of that purpley pink?
Yeah, so when we're looking at an ammonia extraction of an Orchil yielding dye lichen, we are going to get something in that pinky purple range. And that can take anywhere from 2 weeks to a little over a month. It really just depends on all of those factors I was talking about with that, the chemistry you're starting out with, the condition of the lichens, the quality of your water, what kind of ammonia you're using. That concentration can vary greatly between different household brands. You don't ever want to use industrial strength ammonia. Household ammonia is fine.
Thanks so much, Jane. This has been so interesting to learn more about the process and the collection too. So appreciative. We have a question that came in early on, and you may have answered it in the process, but it's about the dye material, Orchil, that you mentioned. What is that name, and how did it get the name?
Yeah, so I believe that Orchil, I want to say that name is coming from one of the English-speaking countries, because I think it's Cudbear in Scotland and it's Corsia in Norway. But I think that it's coming from Orcean, which is that chemical product. Or maybe Orcean is coming from Orchil, but they're related.
Well, couple questions. Do all lichens produce a color that will dye protein fibers? Or are there species that don't produce a dye at all?
There are species that don't produce a dye at all, but there are a lot of dye lichens that are not that do not require an ammonia extraction, and those tend to be more in like the yellow and brown range. So if you are interested in that and you want to pick up a copy of Karen Dietrich Castleman's book, Lichen Dyes, this is still the sort of definitive text. But if you are someone who can read Norwegian, or just someone who wants to take a look at some other fungal dyes, or focus specifically on Norwegian species, there are some dye lichens included in this new book. This is, I think this came out last year, and it's written by Annelise Torkelsen, who is a really, really lovely Norwegian dyer. And in there, she also features some dye lichens that are known for yellow. So we have a, of course, no, I can't find it. But one of the beard lichens is a yellow dye. And she's got the little dye samples down at the bottom. So there are lots of other lichens that can be used for dye. But for purple, you've got to stick with the ammonia method ones.
When you're using the infrared spectrometer, what does the base fiber do, or can it make an impact? If you have a long staple, silky fiber, does that change the way the equipment reads versus a shorter, staple, fuzzier fiber?
Yes, so there is a lot of clamping and unclamping and shifting, also having to do with the density of the textile we're looking at. So sometimes we had to fold something in half and then stick it back under so that we were getting like a robust read. But the nice thing is I can see if it's generating a good spectra in real time. So I can move it around or fold things as many times as I need. So the staple could affect it, yes, but more so in terms of density than um, the actual material of the base messing with the reed.
We have a couple questions just clarifying names of things. Would it be possible for you to type out the different species that you used in the vat, and then also the name of Torkelson's book?
Mm-hmm. So Lissalia postulata is our Norwegian species. That is blerelav in Norwegian. Umbilicaria mammillata. Um, that would be more sort of East Coast US. I do believe we also find it in northern Wisconsin. And then the primary one in this area is going to be Punctilia reducta. There are many, many, many others around the continent and around the globe, but those are the ones I would zero in on.
When we're thinking about responsible harvest and use of lichens, we have a question about just how far does the lichen have to be from its original substrate to be considered safe to collect or dead? So if a lichen is still attached to a branch, but the branch has fallen off the tree and rolled down the hill, is the lichen still alive?
It's alive, and obviously it's because of this symbiotic relationship. The lichen is contained within itself, so it doesn't really need the tree. The tree being snapped off doesn't really affect it, other than eventually that tree is going to degrade and it will sort of crack apart and won't have a substrate anymore. But it is sort of considered fair game, if they're on the ground. And often after a storm, you'll see just chunks of the lichen itself on the ground. And I'm going to say that not all species are equally slow growing. Punctilia reducta is pretty quick for a lichen and also pretty prevalent. So you can look up I use a lot. iNaturalist is a really great resource to find where certain species are in your area and also to check on their sort of ecological health. So it will say, this is a species that is under threat. This is a, common species. And so you can sort of use that to make judgment calls. But what we are not going to do is run around with a knife scraping lichens off of trees. There is plenty after a storm, I assure you.
We have quite a few questions about using bleach to test out in the field. Firstly, what color should bubble up?
Red.
Red.
It will turn bright red immediately.
Okay. And when you do the bleach test, do you need to scrape it away from the outer layer of lichen?
Yep. So you just scrape off that top layer and it, with your fingernail, it's going to come right up. So you just want to get underneath that photosynthetic layer. And then there's that sort of white, sort of fluffy underlayer, and that's where you apply your bleach.
Interesting. And perhaps maybe I don't want to be walking through the woods with a bottle of bleach on me. Would like a bleach pen work, or would you need?
It should be wet. The bleach pens are fine. I've seen people use them. I think you get a better result, and you can get misfires in the field. Like I definitely had at least one where it looked red to me, and then I did a DNA test, and it wasn't at all a lichen that would turn red for that test. But that's why the nail polish, the empty nail polish tube is so clever, and that was actually a tip from Mariah Rogers, who's the president of the Wisconsin Mycological Society, because then it's all neatly contained, and then you have all of the bleach on your brush. Some people use a little vial and just keep Q-tips on them, but then you have to have a bag of bleachy Q-tips. So you can use a little dropper, if you get like the little dropper bottles that tinctures come in. Yeah. So there are some ways to contain the bleach.
You've been talking today mostly about getting color from lichens, but can lichens also be used as mordants? And the person asking the question asked about bearded lichen, Ramalia species.
Yeah, so that is definitely something that I have heard. I have not myself experimented with it. That would be a question for the book, I think. And also, there's the International Fungi and Fiber Symposium. There are a lot of really great resources and people who are working with fungal dyes that know a lot more about it than I do.